Hello everyone. So the second exam does not cover section 9.1, but we're going to get a start on the material in section 9.1. And some of it is, the ideas are pertinent to the exam, so it's nice to talk about at this point. So section 9.1 is on direct products, often called direct sums, direct product, direct sum, whatever it might be. So given groups G and H, we'll say both multiplicative. I mean, you can have them additive too. Recall that G cross H, it's the set of all ordered pairs, little g, little h, such that little g is in group G, little h is in group H, is a group for which little g, little h times little s, little t is equal to gs, comma, ht. 1 is, so that's 1 in G, 1 in H is the identity. And little g, little h inverse is little g inverse, little h inverse. So that's the direct product. So recall the definition. Product, which is a group. The direct product is a group for which, 1, 2, 3. Of course, you can do this for 3 or more groups. Similarly, for is this on? Yeah. For 3 or more groups. So you can define G1, direct sum, G2, or direct product Gn. It's the set of all little g1, little g2, little gn, such that gi is an element of gi. It can be defined for 3 or more groups, and certainly we're not going to cover it because it's really boring. One can show that, like if you did something like this, G cross H, and then you cross it with K like that, is isomorphic to G cross, if you did H cross K first and then cross it with G, so that cross products or direct products are associative, right? So there's no need to write like things like this, little g, little h, little k, right? We just write GHK. Okay, so it can be done for 3 or more groups, and it's all the same as it is for 2 groups. Okay, so one can show that this, which is usually just written as G cross H cross K. Okay, so direct products can be done for 3 or more groups, and it works out just the same as it does for 2. All right, theorem. Given groups G and H, right, 1, G star, which is equal to the set of all little g, comma 1, such that G is in G, is a subgroup of G cross H. All right, and H star equal to the set of all 1H, such that H is in H, is a subgroup of G cross H. All right, so G star, it's the set of all ordered pairs G comma 1 with G and G. And H star, it's the set of all pairs 1 comma H with H and H. These are both subgroups of G cross H. And certainly G is isomorphic to G star and H is isomorphic to H star. Even more than that, okay, not just a subgroup, it's a normal subgroup. Okay, these are both normal subgroups. 2, remember, for subgroups or subsets of a group, right? For subsets of a group, you can multiply them together, right? HK, it's the set of all HK such that H is in H and K is in K, right? You can take H and K's look the same. For subsets of a group, A and B are subsets of a group. A, B, it's the set of all little b, such that A is in A and B is in B. All right, you can take two subsets of a group and take their product. Now, certainly this is the case here. All right, that the product of G star and H star gives you all of G cross H, because G comma 1 times 1 comma H is equal to just GH. All right, so that's certainly the case. 2, 3, G star intersect H star is just equal to the identity element. Right, the intersection of those two subgroups is the identity element. Right, and for G star cross H star is isomorphic to G cross H, obviously, right? Because G is isomorphic to G star and H is isomorphic to H star. Okay, so in a direct product, you've basically got the following. So the proof, you can think about that. They're all just by definition type statements. Given a direct product, okay, given a direct product of groups G cross H, there's an isomorphic copy of G within G cross H, defined in the obvious way. Right? An isomorphic copy of G within G cross H, defined in the obvious way. And you've also got an isomorphic copy of H within G cross H, again defined in the obvious way. And those are normal subgroups of G cross H. By the way, also the obvious thing that you would think is true, that G cross H mod H star is isomorphic to G, the obvious thing that you would think is true is true as well. Again, it's a by definition type statement. Okay, although this is not part of what we're talking about here. Okay, so you have an isomorphic copy of G, an isomorphic copy of H within G cross H. Now, the product of those two subgroups is the whole group. Right? The product as subsets of a group is the whole group. The intersection of those two subsets of the group is just the identity. And, the group is a direct product of those two subgroups. Now, suppose you have a group G. So we want a converse to this, right? Here we have a group that's a direct product of two groups, right? This group is G cross H. Now, given a group G, when can you detect that G is a cross product of two normal subgroups? Okay. So here's the theorem. Let G be a group and N and H normal subgroups of G. if 1, n times h is equal to all of g, and 2, n intersect h is just the identity, then G is isomorphic to n cross h. And this is a important structural theorem within groups. Okay? So compare this to the thing we just proved. Right? In G cross H, all right, you have two normal subgroups, G star and H star. The product of those two normal subgroups is the whole group, and those two normal subgroups intersect in just the identity. Here, it's the opposite, the converse, if you will. G is a group, N and H are normal subgroups of G. If the product of those two subgroups is all of G, and those two subgroups intersect in just one, the identity, I mean, they have to intersect in something, at least the identity, but if they intersect in just the identity, then G is isomorphic to N cross H. Okay, so this is a theorem that allows us to pull apart a group into a direct product. Not that you can always do it, right? I mean, obviously you can't always do that sort of thing, but if it is doable, it can be detected. Okay, and I'll give you a nice example of this. It's with abelian groups, you get a lot of nice examples of this kind of thing. All right, okay. So suppose that N and H are normal subgroups of G, satisfying 1 and 2. So first thing, we want to show that the following is true. So let's show that AB is equal to BA for all A in N and B in H. So anytime you have an element A in N and B in H, AB is going to be equal to BA. Okay, these guys are going to commute. Okay, so here we go. A times B is an element of the left coset, or AH. Right? Because B is in H, AB is an element of the left coset AH. Right? So AB is equal to B0A for some B0, and well, this is because H is normal. Because H is normal, AH is equal to HA. So AB is equal to B0A for some B0 in H. Similarly, AB is equal to BA0 for some A0 in N. Again, because N is a normal subgroup of G. So you can do this kind of thing as well. Okay, so AB is BA0 and also B0A. So B0, actually I think we don't need that one. I thought you needed that statement, but you don't. So AB equal to B0A becomes B equal to B0A. AB is on the left. No, you did need the second one. Okay. So similarly, AB is equal to BA0 for some A0 in N. So, B0A is equal to BA0. So, multiplying on the left, B0A, A0 inverse is B. And multiplying on the right by B0 inverse gives me A inverse 0 is an element of B0 inverse, or equals B0 inverse. Right? So this guy, since A0 inverse is in N, and B0 inverse is in H, right? So the two A's are elements of N. So since N is a subgroup, when you multiply them together, it stays in N. Same for the B's. We get that A0 inverse equal to B0 inverse is an element of N intersect H. Right? But those two subgroups satisfied proposition 2, or part 2, that the intersection is just the identity. So, A0 inverse is equal to B0 inverse is equal to 1. So, right, B is equal to B0. Right, B equals B0 inverse is equal to 1. So B is equal to B0. So AB, which was equal to B0A, is equal to, well, that's just B. Oops, is BA, as required. Okay, so if you take an element of N and an element of H, then they must commute. Their products must commute. They must commute. AB is equal to BA. Okay, now, let's show that for every A, S, and N, and B, T, and H, that A, B is equal to ST if and only if A is equal to S and B is equal to T. Okay, so let's show that for every A and S and N, and B and T and H, that AB is equal to ST if and only if A is equal to S and B is equal to T. Okay, well, AB equal to ST implies, right, put S inverse over here, and then B inverse is over here, or TB inverse, where, right, S inverse A is an element of N, and TB inverse is an element of H, right, because A and S are in N. A and S are in N, so the product of these two things is in N, and the product of these two things is in H. So, since N intersect H is just the identity, we now have that S inverse A is equal to TB inverse is equal to 1. Alright, so S inverse A equals 1, and TB inverse equals 1. So A is equal to S, and T is equal to B, as required. Okay. So far we have that we have shown that every G in G is of the form AB. Okay, so by assumption, every element of the group is of the form AB, where A is in N and B is in H, and this product is unique. Okay, so define F from H mod or H cross K to G by F of A comma B, so that's an element of H cross K, is equal to the product AB. This is surjective, and injective. Because, right, it's surjective because everything in G is of the form A times B, where A is in N and B is in H. That was one of the assumptions of the theorem. Right? N times H was equal to G. So for A and H and B, or A and N and B and H, you can find A and B for every G and G, and it's uniquely so. Right? So it's surjective because everything has this form, and it's injective because we showed it's uniquely. For unique A and B. For every element for every G and G, there's a unique A and B, such that G is equal to A times B. Now we just have to show that it's a homomorphism, and then we have it's an isomorphism. Let's show that F is a homomorphism, and so F is an isomorphism. Okay, so let's look at F of AB times ST. All right, so this is equal to F of ASBT, which is equal to ASBT, right? Where S is in S, or S is in H, right? No, S is in N. I did N first. S is in N, and B is in H. So SB is BS. Right? So this is equal to ABST. Right? SB is equal to BS, which is equal to F of AB, F of ST. And that's it. Right? So F is a homomorphism. That's injective and surjective. Therefore, F is an isomorphism. So we have an isomorphism from H cross K to G. Okay, so G is isomorphic to H cross K. Okay. So there's only two conditions, well, three conditions really, for being able to pull apart G into a direct product of two subgroups. Okay, first you have to have normal subgroups in G, two normal subgroups in G, whose product is all of G, and whose intersection is just one. Okay? Now, before I do an example of that, before we do an example of that, let's explore this condition a little bit. Let's explore that condition a little bit. So, some important properties of the product of two sets in G. Okay? Property number one. So we've been talking about this for a little while now, and now we're going to have a conclusion. One. So this is an exercise for you, and we'll prove that later on. Well, we'll talk about it later on. So prove that for every A and B, well, let's see. Let A and B be subgroups of G. Let A and B both be subgroups of G. So we've talked about when the product of the two A and B is also a subgroup of G. When G was abelian, right? When B was normal or when A was normal, then the product was a subgroup. But there's, a more general statement, and that's as follows. A, B, so prove the following. AB is a subgroup of G if and only if AB is equal to BA. So not that A is a normal subgroup of G or B is a normal subgroup of G, or that the group is abelian. It's just that the product, right, A times B, right, where A times B is a set of all products, little a, little b, where A is in A and B is in B. All right, that's AB. And then BA is the set of all little b, little a, such that B is in B and A is in A. All right, you just want to show that these two sets are the same. So this becomes a subgroup of G if and only if AB is equal to BA. And this is the weakest condition that allows you to get closure of the set AB, right? Because if you take AB and you multiply it by ST, where S is in A and T is in B, then this is A, B, S, T. But then BS, because BA is equal to AB, is going to be A, S0, B0, T. Right, where this is in A and this is in B. All right, so that's going to be your necessary and sufficient condition on A and B, such that the product AB is a subgroup of G. So give that guy a try, and we'll talk more about this later. The other important property is the following: is if A and B are subgroups of G and G is finite. Well, not that G is finite, but yeah, I think G is finite. Then, well, what's the order of that? Okay, there's a nice, neat little formula for that, and that's as follows. It's the order of A times the order of B. Right? It's not A cross B, however, right? The order of A cross B is equal to the order of A times the order of B. Right? But these two subgroups, the A star and B star, they intersect in just one element. So it's like A times B over 1. So here, it's the same idea. You just have to figure out how big is their intersection. Right? So the order of A times B as sets is the order of A times the order of B over the order of the intersection. And let's do a proof of that. That's an important property. Okay. Well, first of all, AB, right, is equal to, well, it's a set of cosets. Right? It's a union of a bunch of cosets. For B equal to B1, B2, so on and so forth. So it's the set of all cosets, right? And since cosets are equal for disjoint, the order of A, B is equal to the order of A times M, where M is the number distinct cosets A little b, where b is in B. Okay, so it's the number of distinct right cosets. So we're not assuming anything that's normal here. We're not assuming A is normal or B is normal. We're just talking about cosets, right cosets. Okay, so the order, so AB, it's a union of cosets, right? And cosets are either equal or disjoint, and they're all the same size. The size of them is just the order of A. Right, we're talking about finite groups here, so everything here is finite. So it's the size of A times M, where M is just the number of distinct right cosets, AB, where B is in B. Okay, well, two cosets A are the same. AB is equal to AC for B and C in B if and only if, well, what's the condition? All right, CB inverse is an element of A. All right, if and only if CB inverse is an element of A. Well, B and C were already in B. So this product, since B and C are in B, CB inverse is in not just A, it's also in B. So AB is equal to AC if and only if CB inverse is an element of A intersect B. Okay? AB is equal to AC for two elements B and C in capital B, if and only if CB inverse is in A. That's just the rule for cosets, right? But because C and B are in B, the product CB inverse is in B. So these two cosets are equal if and only if this product is in A intersection B. So AB is equal to AC if and only if, so the right coset AB is equal to the right coset AB is equal to the right coset AC if and only if CB inverse is in A intersect B. But that's if and only if the right coset of A intersection B by B is equal to the right coset of A intersection B by C. So two right cosets of A are the same if and only if the corresponding right cosets of A intersection B are the same. Therefore, the number of distinct right cosets AB, where B is in B, is the same as the number of distinct right cosets of A intersection B as a subgroup of B. Right? So the number of right cosets of A is the same as the number of right cosets of A intersection B as a subgroup of B. Pretty cool. Right? What is this number of cosets? This number of cosets is, well, it's just the order of the group over the order of the subgroup. Right? The index thing, B index A intersection B. So, right here, now we know what M is. Right? So the order of the product AB is the order of A times M, where M is that number of cosets. Now we know what that number of cosets is. Right? So AB which is order A times M, right, which is the number of distinct cosets, is A B over A intersection B. Pretty cool. As required. Okay, so that's an important, that's actually one of the homework problems in the section, but that's an important one, and that proof is definitely not on the easy side. So we did it. Okay. Okay. So for example, let's leave the example till next time. Okay. I don't want to go too far into it. So next time we'll get right back into section 9.1 and we'll do a nice example of this one. Okay. Alrighty.